my dear students, today we are on measures of variation. In other words, measures of dispersion. Measures of variation means is the measure of how spread out the data is about an average in the data set. In effect, to fully appreciate this, we normally determine how far an average is from each individual element in the data. There are so many ways of measures of dispersion. The common ones are the range, the interquartile range, the semi-interquartile range, the mean deviation, the variance, the standard deviation, etc. But with educational statistics, we will be considering only the range, the semi-interquartile range, the variance, and the standard deviation. So let's proceed. Let's first deal with the range. The range simply means the difference between the highest value in the data set and the lowest value in the data set. For example, given the data 10, 90, 50, 60, 45, and 51, the range will be equal to 90 minus 10, which is equal to 80. And there's a point to note here. The range cannot be determined for a qualitative data. What it means is that it can only be determined for quantitative data. Now let's look at some practical implications of the range. Some practical implications of the range. In the school situation, we can say the pupils finish the class test within 15 minutes. Here, the 15 minutes is the range. That's given the scheduled time. It could happen that not all the people finish within the 15 minutes, but it took a range of 15 minutes. Someone may finish within 5 minutes, somebody may finish within, then the last person to finish may be 30 minutes. And the first person to have finished, maybe finish it within 15 minutes. Then the second practical implication is the teachers made sure that all the pupils left the campus within 5 minutes after closing. You know, as a teacher, you are to ensure the safety of every child in the school. So once it is closing, it is your duty as a teacher to make sure every pupil is not left roaming about the campus. So for that matter, you have to make sure that all the pupils leave the school within the shortest possible time. So here if you say the teachers made sure that all the pupils left the campus within 5 minutes, what it means is that it could be that the first people left the school in some few seconds. The last person left the school in maybe 5 point something minutes. Then let's move on to the semi-interquartile range. The semi-interquartile range Of course, you cannot determine the semi-interquartile range without determining the quartile range. Sorry, the interquartile range. With the interquartile range, is simply the difference between the upper quartile and the lower quartile of the data set. And for that matter, to find the semi-interquartile range, it's a matter of dividing the difference by 2. So in this case, we will get semi-interquartile range being equal to upper quartile minus the lower quartile, all divided by 2. So example, given the data set 2, 5, 3, 6, 7, 4, and 9, then as we learned last week, the lower quartile for this data was found to be 3, and the upper quartile for this data was found to be 7. For that matter, the semi-interquartile range will be the upper quartile, which is 7, minus the lower quartile, which is 3, all divided by 2. And we will end up getting 2. Meaning the semi-interquartile range for this data is 2. Now let's move on to variance. Now let's move on to the next measures of dispersion. That's the variance. The variance is the mean square. The variance is the mean of the squares of the deviations of the observations from the mean of the data set. Now, for the population variance, it is normally denoted by the rho raised to the power 2. And then for the sample variance, it is normally denoted by a slanted s raised to the power 2, as it is indicated. Now let's consider how to calculate the variance from an ungrouped data set, in effect the raw data set. Now conceptually, the variance will be equal to each individual observation, which is xi, minus the mean of the data set, all raised to the power 2. Then after you sum all these deviations up, the squares of all these deviations up, then you divide by the total number of observations in the data set minus 1. Now the total number, so this is portrayed in the next step as indicated here. You see that first we had x1 minus x bar, which is the mean, all raised to the power 2, plus x2, that's the second observation, minus the mean, all raised to the power 2, plus up to the last observation, which is xn, minus x bar, all raised to the power 2. Then all divided by n minus 1. One may ask, why not divided by n, but n minus 1? You know, the sample variance is used to estimate the population variance. That is used to estimate the rho square. So to make the sample variance, that's the value, the sample variance value, as much closer as possible to the population variance, we subtract we subtract 1 from the total number of observation, and statistically it is called the degree of freedom. Now, the detailed explanation of what I have said so far is what is as noted here. Now let me go further. Unbiasedness. statistically, when we say this, we say is to make it an unbiased estimator of the population variance. And unbiasedness here is the desirable property that ensures that the sample value calculated is as much closer to the population value as possible. Now let's consider this example for the raw data. Now we have this data 3, 1, 7, 4, 2, 5, and 6. Now finding the mean, you end up getting 4. Now subtracting the mean from the individual observation and taking the squares of each term as indicated here, then dividing by the total number of observations, which is 7, minus 2, we will end up getting 4.67. Now, the formula above, that is the S squared, being equal to sigma xi minus the mean, that's x bar, all raised to the power squared, all divided by n minus 1, is the conceptual formula. But we have a computationally easier formula to use. And that is given by, it can algebraically verify or prove that x raised to the power, that's the standard deviation, that's the variance, is equal to sigma xi squared minus sigma xi all squared, all divided by n, then all divided by n minus 1. So by this, we take the individual terms. So with the first term, we take the individual terms or individual elements, then we square both. Then after we sum all, and we get 140. Then in the second situation, you sum all the individual terms, and you get 28. And now, noting the total to be 7, when you substitute it into the formula, you will end up getting 140 minus 28, or 28 squared, divided by 7, all divided by 7 minus 1. And you see that we end up getting 4.67 as earlier. Now let's consider the situation of calculating the variance from on-group frequency table. Now with this, let's consider the observations xi being equal to x1 being the first observation, x2 being the second observation, x3 being the third observation, up to xn being the last observation, with the corresponding frequencies fi being equal to f1 being the frequency of the first observation, f2 being the frequency of the second observation, then f3 being the frequency of the third observation, up to fn being the frequency of the last observation. With this, the formula is given by S squared being equal to sigma fi xi squared minus sigma fi xi all squared all divided by Fi, all divided by sigma Fi minus 1. Now, to explain this formula into detail, let's try this example. Let's say you've been given the frequency table below with the individual observations being 50, 20, 40, 30, and 10. Then the corresponding frequencies are 3, 5, 4, 6, and 2. Now, considering the terms in the formula given above, first we have sigma F I times xi squared. So in this case, first we must have our Fi, the corresponding, that's the various frequencies in the table. Then we take the squares of the individual observations. Considering the squares of the individual observations, we will end up getting, that's 50 squared, you will end up getting 2,500. Then 20 squared, you will end up getting 400. Then 40 squared, you end up getting 1,600. 30 squared, you get 900. 10 squared, you get 100. Then what we will do is that with this, we move on to the next one. That's the next column headed by Fi, Xi. With this, you are going to take the individual observations and multiply each by its corresponding frequency. So if you look at the first situation, you multiply 50 by its corresponding frequency, which is 3, and you get 150. You multiply the second observation, which is 20, by its corresponding frequency, which is 5, and you get 100. We do that till we get to the last observation, which is 10, and its corresponding multiplying by its corresponding frequency, which is 2, we get 20. Then from the formula, we have to sum up all these. Then we take the square of all. Then the next step is, you see that the first term in the formula was sigma Fi xi squared. So what it means is that we are going to multiply the square of the individual observations by their corresponding frequencies. So in this case, the first observation, the square of the first observation, we had 2,500. Then when you multiply by its corresponding frequency, which is 3, you get 7,500. In the second situation, we took the square of 20, which we had 400. Then when we multiply by its corresponding frequency, which is 5, we will get 2,000. It happens the same way till we get to the last observation, which is 10. 10 squared, we had 100. Then when you multiply 100 by 2, you get 200. Then when you take the sum of all, you end up getting 21,500. So, now considering the terms in the formula, you see that we ended up getting sigma F, that's the total frequency, which is to be 20 from the table. Then sigma Fi xi, we ended up getting 610. Then sigma, I think there was a mishap in the typing. So the sigma Fi xi is supposed to be equal to 610. Then the sigma Fi xi squared will be equal to 21,500. Now substituting these values into the formula, we will end up getting 21,500 minus 610 squared divided by 20, or divided by 20 minus 1. And with this, we will end up getting 152.368. That's the variance. Now let's consider the case of calculating the variance from the group frequency table. Now with this, there is no difference between this and that of on group frequency table. The only difference is that the class midpoint or the class mark is determined, and each class mark is taken as the original or the single value of each class. Then we use the same formula as in the case of on group frequency table. Then we will end up getting the same thing that we want. That's the variance, our variance. Now let's consider this example. That's the group frequency table below. We have the class 1 to 10, 11 to 20, 21 to 29, up to the last class, which is 46 to 50, and with their corresponding frequencies. Now, in the tabular form, the whole this thing is summarized in the tabular form. You can see that apart from the class mark being determined here, the way the other one was done is the same way as it is here. So you see that you first find the class mark of the individual classes. So in the case of the first class, the class mark is 5.5. And I believe you all know how to find the class mark at this level. Then, taking the class mark as the original or the single observation, you take the square of it, and you get 27.5. Oh, sorry, you get 30.25. Then when you find the class mark of the second class, which is 11 to 20, we will get 15.5. Then when you take the square of 15.5, you get 240.25. Now the same thing happens till we get to the last class, which is 46 to 50. When we find the class mark or the class midpoint, we get 48. Taking the square of 48, it will be 2,304. Now, as we did earlier, you multiply the squares by the corresponding frequencies. So you take the square of the first observation, which is 30.25, you multiply by its corresponding frequency, which is 5, you get 151.25. Then it happens the same till you get to the last class. That one, the square of the class midpoint, we had 2,340. Then when you multiply by the corresponding frequency, which is 5, you will get 11,520. Then we consider the next term. The next term is to multiply the individual class marks by the corresponding frequencies, and we will get Fi xi. And the total, when you sum up the total of the products, you will get 601.5. Now, substituting these values into the into the formula, we will end up getting 21,500 291.25 minus 601.5 all squared divided by 24. Then all divided by 24 minus 1, which will end up getting 270.268 as the variance for the grouped frequency table. Now let's move on to standard deviation. Deviation and variance move together. What do I mean by this? Without the variance, you cannot determine the standard deviation of a data set. What it simply means is that the standard deviation of a data set is the square root of the variance of the data set. So once you know the variance, you can always determine your standard deviation by taking the positive square root of the variance. In effect, it's a matter of just taking the positive square root of the formula as used in the variance. Now, symbolically, the standard deviation is denoted by rho. So you can see that in the case of variance, it was rho squared. So if you take the square root, the positive square root of rho squared, you get rho. Then for the sample variance, for the sample data, we have S. Don't forget, in the case of the sample variance, it was x squared. So if you take the square root of positive square root of x squared, you end up getting S. Now let's try some examples. Now considering the example solved above, remember we had the standard deviation for the raw data. We had standard deviation, the variance to be 4.64. Now taking the standard deviation, it will be square root of 4.67, which is 2.161. Now let's consider the case of calculating the standard deviation from ungrouped frequency table. As we did above, we had the variance to be 152.368 for the ungrouped data. So to find the standard deviation for the ungrouped data above, as we calculated in the case of the variance, it will be S equal to square root of 150 square root of 152.37, which is equal to 12.344. Now considering that of the group frequency table, we use the same formula above. We had the variance to be 270.268, which, when we are to consider the standard deviation, it will be the square root of 270.268, and which will end up getting 16.4398. Now, one may ask, what is the essence in calculating the standard deviation and the variance? It is simply to tell us how spread out the data is. But don't forget, practically, it will not really give you the real view or the reality so far as the data is concerned. But what the standard deviation simply means is that it tells us how spread out the data is. And don't forget, if it's in the case of exams, maybe you conducted a class test or exams on your students and you crowded the marks, the standard deviation can help you to tell whether the students' scores were compact. When I say compact, or they are spaced out. When I say compact, I mean if maybe it happens that majority of the students scored below marks, then it will give you the reality. If it can also tell whether the majority of the students scored above average mark, then it can also tell you whether the scores obtained by the students are uniformly spread out. But it will not, you will not be able, just by looking at the standard deviation, to tell whether the students scored below, or they scored above, or they scored average, or their scores was spread out. But what we can say is that the lower the standard deviation, the less spread out the data set. And the higher the standard deviation, the more spread out the data set. Now you remember under the graphical illustration, we were trying to determine the shape of the data set by using histogram or the graphs, precisely histogram. Now we can also use a numerical value to determine the shape of the data set. And this numerical value or entity is what we call coefficient of skewness. Coefficient of skewness, and it is symbolized this way. Now the coefficient of skewness simply is the numerical measurement of the shape of the data set. And it is normally given by 3 bracket open mean minus the median bracket close divided by the standard deviation of the data set. Now the coefficient of skewness normally takes the range between -1 to +3. The coefficient of skewness normally takes the values between -3 to +3 inclusive. When I say inclusive, I mean the endpoints are included. And this is mathematically indicated as -3 less than or equal to coefficient of skewness less than or equal to +3. Now let's look at the individual interpretation. Whenever you end up getting the coefficient of skewness to be equal to 0, then the distribution is symmetrical. In other words, it is normal. Thus, you have half of the total number of observations falling below the falling below the median, and half of it falling above it. And when it happens like this, you always get the mean, the median, and the mode of the data set to be equal. The coefficient of skewness is greater than 0. It means the mean of the observation is greater than the median, and as such, you end up getting a positive value. And this indicates that the data set is positively skewed. And if you remember when we were dealing with the graphical illustration, whenever a data set is positively skewed, especially in the case of students' exam score, then it means majority of the students scored low marks. Now, when the coefficient of skewness is less than 0, then it means the distribution is negatively skewed. What it means is that the median is greater than the mean, and as such, you end up getting the coefficient of skewness to be negative value. And when it happens like this, it means in the case of exam scores, it means that majority of the students scored higher marks. Now let's consider, let's say in the situation of an exams, we had the mean score being 25.063, the median mark being 19.25, and the standard deviation being 16.4398. Then substituting the values into the formula, you will get 3 bracket open 25.063 minus 19.25, all divided by 12.344. And we will end up getting 1.413. And since this is positive, it means the data set is possibly skewed. Which also means majority of the people scored below average marks. Now, I'd like you to go and try. Now, there's one point you should note before anything. The coefficient of skewness is also used to compare two data sets. In other words, it could be even 2 or more data sets. Now, let me briefly explain this. Now, let's say you organize an exam for your pupils for the same subject but 2 different classes, and you want to know which of the classes perform better. First, you calculate the coefficient of skewness. If you end up getting the coefficient of skewness of the 2 data sets to be positive or positive, then you consider the one with the highest positive value. Normally, the one with the highest positive value means that that class performed lower than the other class. If it happens that you had both classes getting a coefficient of skewness being negative, then you consider the one with the highest negative value. And that means the one with the highest negative value performed better than the class with the lowest negative value. But if it happens that the coefficient of skewness for one class is negative and for the other class is positive, then definitely those with the positive coefficient of skewness performed worse than those with the negative coefficient of skewness. If it happens that all scored or they had the coefficient of skewness to be 0, it means their performance are normal. That their performances are normal. Thus, you can't tell which one performed better than the other. Now, I want you to go and try these examples. Now, this is the lives of 40 transistor batteries to the nearest day in a school. That's the data given. Then with this, using a class interval of 20 to 29 and so on, you are to construct a frequency distribution table for the data. Now from the data, you are to calculate the mean life of the batteries in the distribution. Then the next II, calculate correct to 2 decimal places the standard deviation of the data set and interpret your results. Now IV, that is the fourth one, you are to calculate the coefficient of skewness for the data, determine the shape of the distribution, and hence interpret your results. You are to deal with question 2 as well, then question 3. Now, our next topic will be measures of relationship. And for the sake of time, we will pause here and continue next time. I hope you enjoyed the lesson. Good day.